In this unit, we look at how we can use nucleophilic substitution reactions, that is the Sn1 and Sn2 reactions, to convert alcohol starting materials into alkyl halide products. Let's take a look at how this reaction takes place. In order to convert alcohols into alkyl halides, what we are going to rely on is the use of halogen ions, in other words, halogen anions, as our nucleophiles under acidic conditions. So the way that this will work is that we'll start with our alcohol material, with our alcohol there, and we'll treat this typically with directly a halo acid, such as HCl or HBr. And let's take a look at what happens here. So anytime we have acid present, we expect that the first step of the mechanism that we see will be protonation. And so indeed, what we're going to do here first is protonate. And when we look for what to protonate from the organic molecule, we're looking for lone pair electrons or pi bonds to act as the proton acceptor. So checking out what we have available here, we just have the lone pair electrons on the oxygen. There's no pi bonds, and so there's only one option here for what we can protonate, and that is we're going to plug that proton onto the oxygen atom. And that's going to force that hydrogen-chlorine bond to break, freeing chloride anion as a result of this reaction as well. So that's going to give us chloride anion, which we certainly recognize as a good nucleophile. It's also going to give us our protonated alcohol as an intermediate here. So we have OH2, we have a lone pair of electrons on the oxygen and a positive formal charge there. And then at this point, what we have accomplished here by protonating the oxygen is we've created a much better leaving group, because if we break away this OH2, the product of that breakage of the carbon-oxygen bond here is going to result in release of water. Water is a very stable product relative to just breaking away the hydroxy group without protonation first. So we protonate first so that we create a much better leaving group to make this reaction more favorable. So step 2 is going to be that the leaving group breaks away. And this assumes that we're doing an Sn1 reaction, which is certainly a reasonable thing to do at secondary or tertiary carbons. At primary carbons, we're going to have to take a slightly different route, because if we just break away the leaving group without something else happening simultaneously, we'd be left with a primary carbocation, which is a big no-no. But here, we break away the leaving group and we're left with a secondary carbocation, which is okay. But you do want to be on the lookout for carbocation rearrangements, so keep an eye open for carbocation rearrangements if possible. In this case, there are no carbocation rearrangements possible, so therefore we continue onward to the next step. And thinking about what we know about nucleophilic substitution reactions and carbocations and all that business, a common thing that we have seen happen in the past is that when we generate a carbocation intermediate, it gets attacked by a nucleophile. And that's exactly what's going to happen here. So we look around at what do we have available to be the nucleophile. And what we see is that we have chloride anion. And chloride anion is certainly a very capable nucleophile. And so in step 3 here, the nucleophile, that halogen anion, is going to attack the carbocation. Opposites attract, so we have that negatively charged chlorine attacking the positively charged carbon. So we get the chloride staging its attack right now as the nucleophile, coming in, forming a new covalent bond to that carbocation to lead us to our final product of this particular reaction. Now we do have a newly created chiral center here in the final product, so I need to remind you here that regardless of what the stereochemistry was of our starting material, regardless of what the stereochemistry was of that carbon that's bonded with hydroxy group, we would expect this product to be a mixture of the R and S enantiomers. So we'd expect this to show up as both a wedge and also within the reaction flask, a dash going to that chlorine as well. So showing the stereochemistry of this, we'd have two different stereochemistries there to the chlorine. And the reason for that is due to the fact that our intermediate here, right here, is planar. And since it's planar, meaning laying flat, that means the chloride anion can attack from either the top face of the molecule or the bottom face, thereby giving rise to the chlorine either oriented toward you or away from you, or in other words, showing up as a wedge or a dash in the final product. So let's take a look rather than the Sn1 reaction, which is what we see here, and hopefully you realize this was the Sn1 reaction because the Sn1 mechanism is the mechanism where the leaving group leaves first And then as a second step, the nucleophile attacks. We can also do the Sn2 reaction, which is going to be the preferred route to go if you are working with a primary carbon, because primary carbons can't make a stable carbocation. So here we have the case of a primary carbon alcohol reacting with HBr. Let's take a look at what happens here. So our hydroxy group is going to get protonated by the acid at the very first step of the mechanism, which we'd call, of course, protonation of the organic molecule. And then the hydrogen-bromine bond breaks, like so, giving way to our organic intermediate, which will be staged with water leaving group there. Now that it's picked up that extra proton, we have OH2+, and bromide anion, Br-, like so. And then what will happen at the next step is, due to the fact that this molecule can't form a stable leaving group, can't form a stable carbocation once the leaving group leaves, what's going to happen is that the nucleophile attacks at the same time the leaving group leaves. So we could think of this second stage here as being the very typical Sn2, which in other words is nucleophile comes in and attacks the electrophilic carbon, that's the positively polarized carbon right there. At the same time, the water group breaks away to lead us directly into our final product here. So due to the fact that we aren't forming a carbocation, we can't get a carbocation rearrangement in this reaction, and we'll get onwards to our final product right here of this Sn2 type reaction. Let's do one more example of these types of cases of reactions to solidify that we know what we're doing here. Okay, go ahead and take a look at this example problem and try to predict what the product would be, then we'll go through the answer together. Looking at this problem, first thing that we would expect to happen here is protonation, of course, because we have acid presence. And we look at protonation of the alcohol group because that's going to be what has lone pair electrons or pi bonds. So we bring the lone pair of electrons from the oxygen over, grab that proton, forcing the hydrogen chlorine bond to break, and giving us our intermediate here with our hydroxy group now converted into a much more capable leaving group of water. So we have now the molecule set up with a nice leaving group. Now what will happen next, since we said this is an Sn1 reaction going on, is that the leaving group will break away, break that carbon-oxygen bond like so, taking the electrons onto the oxygen to give us water as a product of this reaction, as well as our carbocation. So we go ahead and plug in our positive formal charge right there in our trigonal planar intermediate. And then keep in mind that carbocations are generally subject to rearrangements if there's a 1-2 shift that we could do in order to stabilize that carbocation. Indeed, here there is. So there would be a hydrogen bonded to this carbon right here, and that can move over from that position over one spot, hence a 1-2 shift to here, to end up resulting in the carbocation residing right here once we do that migration. So now we take that rearranged carbocation, and at this point, this is where we're going to bring in our nucleophile. Our nucleophile was that chloride anion that was released up here. So we bring that guy in, as well as its lone pair electrons, of course, doing the work here. We take our electron pushing arrow, started at those electrons, finish up, very importantly, on the atom here to make an accurate map. And that's going to lead us to our final product of this Sn1 type reaction. So we'll go ahead and plug in that chlorine atom. And now at this point, our final product has no chiral centers, so we don't need to draw multiple versions of this or anything like that. If this did have a chiral center there that we just created, we would need to draw the chiral centers with a wedge and a dash. But here, since there's no chiral centers, no need to draw any stereochemistry in there. There's just one stereoisomer of this molecule. Now, I will warn you of one twist that you will sometimes see in these nucleophilic substitution reactions, and that is sometimes rather than using HCl or HBr, an alternative is going to be to use sodium chloride rather than HCl. And if we do that, sodium chloride is not itself acidic, and so therefore we would not be able to do the protonation step, and therefore the reaction would take place very, very slowly. So rather than just using sodium chloride, instead you can use sodium chloride and sulfuric acid. So the sulfuric acid would enable that protonation step to take place, and then the chloride from sodium chloride acts as the nucleophile. So that's an alternative route that you can accomplish the same outcomes that we've seen above, reacting with sodium bromide or hydrochloric acid. So an alternative to HBr, of course, would be using sodium bromide and sulfuric acid, H2SO4. So just keep that open flexibility of thinking here. And hopefully at this point, if you were to come across sodium chloride and sulfuric acid, you would kind of be able to limp your way through the mechanism, even if you didn't know exactly what was going on, because you would know that you needed to use that sulfuric acid to protonate the alcohol, and that chloride could certainly act as your nucleophile. So do keep those alternatives to HCl and HBr in mind for doing these nucleophilic substitution reactions.